We did PID controllers. What is a PID? A PID is a type of control algorithm which uses three components, proportional, integral, and derivative, to achieve a desired output for a system. The proportional aspect measures the difference between the desired output and the actual output and produces a system response proportional to this error. The larger error, the larger the response. This alone is not always enough to remove the steady-state errors, however. The integral component is capable of addressing the steady-state error as it produces an output signal proportional to the integral of the past error over time. The longer the system has been running, the stronger the integral response. The derivative takes into account the rate of change of the system and produces a response based on the expected future state of the system. This helps to avoid overshoot and oscillations. Combining the components and application. The three responses of the components are then combined by the controller to produce the total output signal. The individual contribution of each component may be increased or decreased through a process called tuning. Different systems will require different degrees of each component. PID controllers are used in an array of fields such as temperature regulation, flow control, systems, motor speed control, and robotics. We will now look at the app that we have developed. So in the top left, you can see our graph for the PID controller response. If you click the Generate Graph button on the bottom, you'll be able to see a line appear that shows the response of the controller. Under that, we have the tuning components for the PID values. You can set the value of each, how strong you want each component to be. So proportional obviously sets the proportional component, same with the integral and the derivative. In the top right, we have the disturbance characteristics. These alter the disturbance to the signal. You can change the magnitude, which changes the absolute value of the disturbance. The amplitude changes the peak value of the disturbance, and the frequency obviously changes the frequency of the disturbance. The time range and desired value. The time alters how long you want your simulation to go for. So if you set it to high, you can see what the system will do further in the future. And the set point changes what value you want the system to approach over time. This is the value that the PID controller will attempt to reach. I'll now pass over to Nuvin to show the controller working.
All right, thanks, Matthew. Now I'm going to produce a controller response by setting the PID values, the time range, desired value. As you can see, we have produced a controller response which is pretty underdamped. So as you can see from the output text box, we have produced a proportional value of 1.89, an integral value of 31.86, a derivative value of 0.79, as well as the desired value of 59.69, which is essentially the set point. A maximum value of 82.3, which is the maximum value of the controller response. The overshoot of 37.87%, which is the percentage overshoot, which is the maximum percentage by which the system output exceeds the set point before reaching a stable value. As you can see, the noise amplitude, magnitude, frequency is not set, so we have zero display. The settling time of 4.84 seconds, which indicates the settling time of the system, and it is the time taken for the system output to reach and stay within a specified range around the set point. And lastly, we have an array of error values, which is basically like the value at each time step during the simulation. The error is calculated as the difference between the desired value and the actual system value at each time step. These output parameters provide valuable information about the behavior and performance of the PID controller and can be used for analysis and tuning purposes. So now I'm going to demonstrate to you guys what how applying disturbance will affect the controller response. A- as you can see, like the controller response, so we have produced a different maximum value of 85.82. The overshoot value has increased significantly to 43.77. And now we have displayed the magnitude, the magnitude of 5.1010, amplitude of 1.53, as well as a noise frequency of 9.69 hertz. And surprisingly, the system has taken a lot less time to settle down. And as previously demonstrated, like these are the error values and the array of error values. So I will try uh, changing the frequency to see if we can get a better response. Right, so this time around we have a better response. See how it has affected the parameters. So this time the maximum value is 75.41. The desired value is 59.69. Uh, and this time the overshoot is a lot less, 26.33%. And the noise magnitude is same as magnitude and amplitude is same as before, but this time the noise frequency is set to 99.74. And this time the settling time has increased to 5.97 seconds, which indicates the time the system has taken a lot more to settle down. And so yeah, so basically this is our app, and I would like to hand over to Matthew to conclude our presentation. Thank you.
All right, thank you for listening and watching our presentation. Hope you enjoyed our PID controller. Very useful for regulating systems. All right, goodbye.